So this is lecture number 21 and 22 of Introduction to Physical Metallurgy class. So today's topic is completely a new topic where we'll discuss about solidification. And solidification itself is a one semester course, right? But in this Introduction to Physical Metallurgy, we'll come across with some important points only. To the technical points. First, in the today's lecture, we'll be talking about what is solidification, how it occurs, right, and what are the macrostructures form after solidification. Those things we'll discuss today. In the coming lecture, we'll talk about the mechanism part completely, mathematical part. So, okay, what is solidification now? Suppose the question is, what is solidification? The name itself is saying solidification means the liquid will become solid in a simple way, I can say. That means it is a kind of phase change in phase, or you can say phase transformation, because solid is one phase, liquid is another phase, right? Since we are metallurgists, we'll talk about solidification of metals and alloys, right? So that means the liquid metal will become solid, or liquid alloy will become solid alloy. That is called solidification. So it is a phase transformation process. So, and okay, fine. So before moving into the topic, let me show you video, so it will be more clear. Okay, this one. Okay, just okay. So just have a look, This is a YouTube video, and just have a look how solidification or what is solidification. So you have seen that what is happening exactly. Melting is happening, and they are finally pouring the molten metals or alloys into a particular mold. Huh. So inside the mold, solidification will happen. The liquid will become solid, right? The heat will be get extracted by the mold and the heat will be dissipated to the environment, and the liquid temperature will reduce, and finally it becomes solid. So basically, what happens? Okay, let me show you this one. Yes. So basically, what happens? Uh, if you remember, in metallurgy, we have a subject called principles of extractive metallurgy, or that is, we have also non-ferrous extraction. So metal extraction, when we are doing, we are extracting metal in form of liquid, basically. If you remember, right? Because basically the mechanism behind the metal extraction is the smelting process, right? We are doing smelting. That means we are doing reduction and melting. So finally, we end up with a liquid metal, and we convert the liquid metal into alloys by addition of alloying element, right? And finally, we get a liquid alloy, for example, or we sometimes get a liquid metal. So, but the liquid metal do not have any kind of applications. Basically, we need a solid metal for our applications or solid alloy. So we need to do solidifications, right? We need to convert this liquid metal into solid. So how it is done? By using molds, right? So solidification will be happen inside a mold, and mold will be what? Mold will be a metallic materials, or it may be a ceramic material, basically, right? It has a definite shape. So the liquid metal will be poured into the mold, and it will take a shape when it solidifies. Finally, you'll end up with a solid metal having a particular shape. You can process this solid metal further to get any other dimensions, right? You can get a plate, sheet, coils, rods, anything you want, right? So solidification is very important, right? You can see just this is a liquid metal in this image, and this is a mold, and liquid metal is poured into the mold. You can see this is the diagram of a mold, and now solidification has happened. This is solid. And finally, if you want to look into the microstructure of this particular solid product, this will be like this. Can anybody tell me what we can see in this solid product? What is visible? This is a microstructure, I'm saying, huh? So what is visible here? Just carefully look.
Grains.
Yeah, very good, excellent. This is a metallic material, so we can able to see the grains, right? These are one grains, but some are looking like dark, some are brighter, due to this contrast, huh? Due to this, maybe due to different in orientations, they get attacked by in a different way by the acids, by the HMs, huh? Fine. So this is the microstructure of a solidified metal or alloy. Fine. Okay. And this is a mold, as I told, and we are doing pouring. Fine. See, we can have, and this entire process is called casting process, technically, right? Casting means we are pouring the liquid metal into the mold to get a solidified metal or solidified alloy. This process is called casting. Sometimes the product, the solidified product often is also called casting. Some people call it. Or maximum people call it as a ingot. Hmm. So we can have two types of casting. One is batch casting, one is continuous casting. So in industry, we basically prefer continuous casting. But the video you have seen just few minutes before, that is a batch casting. Batch means you will have a mold, you pour it into the mold, that's all, right? And when it will solidify, you take out the solidified metal or alloy, right? But continuous casting means you are continuously pouring into the mold, and you are continuously withdrawing the solidified metal or alloy. That is a continuous process. In industry, we prefer continuous process. It has lot of advantage. This is not the right time to discuss, huh? There is a different subject is there in the higher semester, you will study all those things, fine. Okay. Now just have a look. As you people have understood, after solidification, we'll get a grain structure, right? We'll get grains and grain boundaries, obviously. In right. So just have a look how grain is forming at the end of the solidification, right? Or during solidification, how grain is forming, right? Just have a look. This is a liquid metal, for example. This is a liquid metal, but in the liquid we have certain solid which is forming. This is one solid. 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 But this entire is a liquid, right? So this solids start forming at random places, basically. Random places. So that solid actually is called crystallite. That is called crystallite nuclei. You have to remember. So you have a liquid metal. Now a crystallite nuclei is forming at a random position inside the liquid, which is nothing but a solid particles, right? Then you can see this crystallite nuclei start growing. This is start growing. It has been increased in size. This one is this one, right? This one is this one, and this one is this one, right? And these two are this. So now this solid crystallite nuclei is growing inside the liquid. That means what? Liquid will get disappear and this solid will grow, right? So further growth is happening. Just have a look. Third image. And fourth image, further growth is happening. Finally, further growth is happening. But here you can see some interesting point. Just see this this crystallite nuclei is now becoming a crystal. So this crystal and this crystal is meeting at a point at this junction. They're meeting, and this crystal is also meeting at a point. So crystallite nuclei has grown into a crystal, individual crystals, and they are meeting at a point due to growth. Fine. Now you can see they are meeting at this point. These two crystals are meeting at this point. This crystal and this crystal will meet at this point, right? This crystal and this crystal is meeting at this point, right? So finally, you can see lot of meeting has been happened here due to the growth only, right? And finally, entire liquid will become solid, and that is made up of grain and grain boundaries. So this is one grain or this is one crystal, and this is the grain boundary. You can see, right? Because this is another crystal. This is another crystal, or this is another grain, right? This is another grain. This is another grain, and this is the grain boundaries. So you people have understood how grain boundary is forming. It is okay up to this.
Yes, sir.
Yes, sir.
Fine. So grain boundary is forming when two different crystals are meeting, because on the when they will meet, they cannot grow further. They will stop because both are solid, right? So again, I am saying initially we have a liquid metal. When we lower the temperature of the liquid metal, what happen? A time will come when solid particles will start forming randomly inside the liquid, right? Those solid, small, solid, tiny solid particles are called crystallite nuclei. And these crystallite nuclei then start growing inside the liquid, right? When they grow, they will meet to the adjacent crystals, which is growing, also growing. When they meet, they will stop in that position. In other direction, they can grow, right? Now, finally, what happens? Where they meet, that will become a grain boundary. And individual crystallite nuclei will become a grain, or you can say crystal. Fine. So this is the scenario. Now, already, I remember this image has been discussed earlier, if you remember, right? But again, I would like to discuss over here, right? So just imagine this is a microstructure of an ingot. As I told, ingot is nothing but a solidified metal, right? Or solidified alloy, anything you can say. So this is a microstructure. That means we have grain and grain boundaries. Just you can see lot of grain and grain boundaries are present, and they have different orientations also. Each grain have a different orientations. And this kind of microstructures of a ingot is called equiaxed grain structure. You have to remember. Equiaxed. Equi means equal. Axed means every axis they have grown in equal dimension, you can say. But some people call equiaxed grain as a grain with random orientation. You can just have a look. All the grains are not oriented in same direction. Since I have taken a small portion, so it is looking like they have the same orientation. But exactly, just look at this grain, this grain, this grain, right? This grain, this grain. They are oriented differently, right? So grain with random orientations, right? So we have a ingot which is a solidified metal or alloy having a equiax grain structure. So what will happen to the grain structure after rolling? After basically cold rolling. Cold rolling means rolling below recrystallization temperature. That means you can suppose understand at the room temperature you are rolling. So you can see this ingot is there and it has been passed through roller. This is the top roll, this is the bottom roll, right? It is passed through the roller. Now what is happening? This is the new structure which is obtaining. Same grain boundaries is present. Anybody remember what is happening here? Just compare the image of this one and now this one. What is happening to the grain? This initial
Sir.
grain is this one, and this is the, yeah. Yeah, you can speak. It is clearly visible. The rolling direction is this one from here to left to right. So what is happening? The grain is getting elongated in the rolling direction. Yes or no? Just have a
Yes,
look.
sir.
Right? The grain has been elongated in the rolling direction. And due to this thing, what is happening? The grain is getting what? Oriented in a preferred
Particular
direction.
direction.
Very good. The grain is oriented in a preferred direction now because initially the grain is in a random orientations. Now due to rolling and rolling have a particular direction, the grain has been elongated and they have oriented in a preferred direction. You can see from left to right the orientation is now, right? So how many of you remember a individual grain is anisotropic or isotropic? Let me see who can answer. So this is a polycrystalline material, right? So a individual grain of a polycrystalline material is isotropic or anisotropic? Nobody remember?
Anisotropic.
Very good, anisotropic. Excellent.
Anisotropic.
Yeah. So individual grain or a single crystal is an anisotropic. Anisotropic means if you move in different crystallographic directions, the same property will be different. Suppose I am talking about bulk modulus, modulus of elasticity. If you measure the modulus of elasticity in x-axis and you go in y-axis, it will be changed. Material is same, but with different crystallographic direction, the property is getting changed, right? If you remember, I already have explained why. Because of atomic spacing, distance between the atom is different. Lot of things I have explained. Suppose I am talking about magnetic property, electrical property, maybe the mechanical property itself, it will be changed in different direction. So that is anisotropy. But if you remember, if you have a polycrystalline materials and they have a equiax grain, so entire material is isotropic or anisotropic? In a polycrystalline material, entire material is isotropic or anisotropic?
Isotropic.
Isotropic, very good. Because the anisotropy will get cancelled out because each grain is oriented in a different orientations, right? And individual grain is anisotropic, but if you have a multiple grains, it will automatically become isotropic, right? But just tell me, if I will consider this part and this part, what is the difference? I'm considering this one or this one. This one, I'm considering the property of this one and property of this one after rolling. Just tell me. Both are isotropic or both are anisotropic or something is happening after rolling?
After rolling, anisotropic.
Very good. Excellent. So initially you have a random orientation of grain and this is a polycrystalline materials. That's why it is isotropic. But the moment you are rolling it, the grain is elongated in a preferred orientations, preferred direction. Automatically it will become anisotropic, right? Because of this preferred orientation. And this concept is called texture. Texture means the grain with preferred orientations. We can obtain the orientations using lot of things like we can do XRD, we can go for those EBSD methods. About XRD we may discuss in the coming lectures. Okay, fine. And just have a look. This is the microstructure. This is just an what animation image. But this is a real image. You can see the grain has been elongated in this direction, right? This is the initial grain having random orientation, but due to rolling, the grain has been elongated in this direction. You can see because the thickness has been reduced due to rolling. The thickness is higher here before rolling, right? The same magnified image has been shown over here. You can see grain with random orientation. You are doing rolling. Now the grain has been elongated in a particular direction. Okay. Anyways, now we'll talk about solidification of liquid metals and alloy in polycrystalline materials. Already I have told about what is solidification. Now the question is temperature just at solidification. So when solidification is happening, that means liquid is starting to convert into solid. What is happening to the temperature? You have to remember, if it is a pure metal, then during solidification or at the point of solidification, the temperature remain constant. It is a fixed temperature, right? But when entire liquid will become solid and solid will be cooling to the room temperature, again there will be a temperature profile, right? I may show you in the coming lecture also this part. And solidification carried out. Solidification is carried out in the mold, as I have told. It may be a metallic mold, it may be a ceramic mold, right? Because ceramics have very high temperature, no problem. And some metals have also high temperature. You can use metals as a, and if you are using metal as a mold, the solidification will become faster. Can anybody tell me why solidification will become faster if we are using a metallic mold rather than a ceramic mold? Let me see how you can imagine. Nobody have remembered the properties of metal and ceramics? About the conductivity, thermal conductivity?
The ceramics have high boiling point.
No, that is not related. I'm talking about conductivity, thermal conductivity. Solidification means you are not getting my point. Solidification means liquid will become solid. How liquid will become solid? If the temperature will be reduced. If you reduce the temperature of a liquid, right? Below the melting point, it will start becoming solid. Or below the liquidus temperature for a alloy, it will start becoming solid slowly. Because metals have high thermal conductivity. That means it can extract the heat quickly from the liquid and it can dissipate the heat to the environment again at a faster rate. It is okay? You people understood? But
Yes,
in
sir.
case of ceramics, the thermal conductivity is not so good. It cannot extract heat at a faster rate, or it cannot dissipate the heat to the environment. That's why. Okay, anyways. So name of the product after solidification, as I told, it is called ingot. Or some people call casting or cast product. Solidification direction. Okay, I'll show you solidification direction from cast structure of a pure metal. Okay, I'll show you those things. Okay, just have a look. So this is a mold, and mold have cope and dry. We'll not discuss that. This is a mold. Just imagine this is a mold, and we are pouring a liquid metal into the mold, and we want to form this kind of structure after solidification. As I told, mold is nothing but where the solidification will happen and where it has a particular shape, because the liquid has to solidify in a particular shape finally. So we are pouring the liquid metal or alloy into a mold, and finally we are doing solidification. Now just have a look. This is an image showing solidification actually. So this is one of the cross section. So this part is showing you, this brown part is showing you the mold part, the mold. And this is the mold wall, right? Wall of the mold. This one. This is the wall of the mold, and this is the entire mold. I have taken a one cross sections, right? Now just have a look. This is this dark part. This is the solidified metal or alloy, right? You can see initially at the mold wall, the grains are very smaller. But if you go to the center of the liquid, the grains are bigger, elongated grains. I will discuss that soon. So the grain which forms at the wall of the mold are equiaxed grain, but they are small in size. Fine. But the grain new grains which forms on these initial grains are elongated one, and they are elongated towards the center of the liquid, right? This is one of the cross section only. If you are considering the top portion, then the growth will be in the downward direction. If you take the right side part, the growth will be towards left. If you take the bottom part, the growth will be upward, right? So this is just a cross section part. And just have a look. This is a plot between temperature of the liquid and time of the liquid, or temperature versus time. This is a cooling curve. You can say this is nothing but a cooling curve for solidification. You can see TL is the liquid temperature, the liquid, and this is the melting point. This horizontal dotted line is the melting point. So this is the liquid temperature initially. When you are cooling, the liquid temperature will go down like this with time, right? The cooling will be very fast, right? And when the temperature reaches to the melting point, the temperature become constant. Just have a look. As I told, during when solidification is happening, temperature will not change. It will become constant. Basically for metal, pure metal. Basically for pure metal, right? Because it has only single constituent. That's why. When solidification will be end, again the solid will cool at a faster rate. Just again there will be a temperature profile like this. And finally, this is the room temperature, right? So this part is showing you solidification only. That means at this point, the solidification will end. That means at this time, solidification will completely end. But solid have higher temperature. It will cool down to the room temperature like this, right? Now this is a image showing you dendrite. I will discuss that again. Just wait. Huh? So again, just this is a mold wall. You can see this is the wall of the mold, but a dendrite is forming. Dendrite is nothing but a tree-like structure. Like the main structure of the tree is vertical, but that is trunk. You can say from that trunk, many branches are coming out, and from each branches, new small branches are coming out, right? That is a tree structure. So this same structure is obtained during solidification sometimes, but this happens when we are dealing with alloys or when we are dealing with a metal containing impurities, basically. But basically for a pure metal, we sometimes see dendrites or sometimes we may not see dendrites. Dendrites are obtained when we are dealing with alloys or when we are dealing with metals containing impurities, right? Basically, I'll discuss that again. This is the structure, dendritic structure. Just have a look. Like you can see the tree-like structure is present. Initially, it was entire liquid, but upon solidifications, we are getting dendritic structures, tree-like structures. Lot of branches are present. So this is one branch. From one branch, lot of small branches coming out. See, this is the one branch, and a new branch is coming out. This is one branch. This is one branch, and from new branch, new small branch are coming out, right? So we can have a primary dendrite, secondary dendrite, and tertiary dendrite. Primary dendrite means one single branch. From primary dendrite, new branch is coming out that is perpendicular to it. That is called secondary dendrite. And from secondary dendrite branch, new branch will come out perpendicular to the secondary dendrite. That is called tertiary dendrites, right? Now I will explain that why this dendrite formation is happening. Okay, before discussing that, just imagine, Just imagine this is one of the situation. What is this situation? This red portion is the liquid and this blue portion is the solid, right? That means initially entire thing is red, right? Because everything is liquid. But when we cool down the liquid, the solid will start forming. Suppose this blue color is solid is forming, right? You can see at a particular positions, a bump is forming. I'll discuss that. That is called this one, protuberance. Protuberance means it is a disturbance. A disturbance will form as a bump at the liquid and solid interface. This is a interface, right? Interface is nothing but the boundary between solid and liquid. So at the interface of solid and liquid, a protuberance is formed, which is a disturbance. This protuberance may dissolve or it may preferentially grow, right? So in this situation, it is getting dissolved actually. But here you can see this protuberance is forming and it is growing in that particular direction. Other things is liquid, but that particular protuberance may grow in this direction. And this is actually a dendritic structure. This is the first initial dendrite, and this perpendicular portion are secondary dendrites. Right? So I will explain why. So that means in this kind of solidification, the first image, we will get a planar interface. Interface will be completely plane, if you consider. But in this situation, the interface is not a planar one, not a plane, because in a preferentially particular location, the growth will be happening. That means entire interface is not growing. The entire solid interface is not growing here. At a particular location of the solid liquid interface, the growth is happening. That's why it is forming a tree-like structure. That is called dendritic structure. Fine. I will explain why this is happening right now. That's why the topic is solidification in metals and alloys and morphology of the growth. Okay, fine. So the question is formation of planar interface. How this planar interface is forming in a pure metal. So suppose the first condition is you have taken a pure metal, right? There is no impurities, right? So during the solidification of a pure metal, two chances are there. Dendrite may form or dendrite may not form. If dendrite will form, that means the planar interface is not stable. If dendrite will not form, then planar interface will be there. There will be no preferential growth actually. Fine. So condition 1. What is the condition 1? When mold temperature is low, then the molten metal. Suppose you are using a mold and the temperature of the mold is very low, right? Suppose room temperature. Consider it at a room temperature. But the liquid metal is at a very high temperature. You now need to pour the liquid metal into the mold. And in this situation, maximum chance is there will be formation of planar interface. Right? The solid and liquid interface will be completely plane. There will be no preferential growth. So there will be no formation of dendritic structure, basically. Fine? So this is actually due to positive that is, you can say, positive temperature gradient. The condition is positive temperature gradient. Why positive temperature gradient? Because you can understand the solid temperature will be always low, liquid temperature will be always high. Right? So there is a gradient in temperature. Okay. What I have written, when solidification starts at the interface, forms between solid and liquid, and a protuberance will form in the solid, and this will get dissolved since the liquid temperature is higher than the solid, leads to stable planar interface. Again, I am saying a stable planar interface will form when the mold temperature is very low, but the liquid temperature is very high, right? And when the protuberance will form, it will again dissolve. It will not grow preferentially. Entire interface will grow. The protuberance will not grow, right? Because the liquid temperature is high, that's why this protuberance which has been grown again dissolved into the liquid, right? So that means this bump will dissolve because the liquid temperature is high. This solid will not grow preferentially. The entire interface will grow, right? Okay, next situation, condition 2 for pure metal. When mold temperature is high, near to the fusion temperature of the metal. That means, just imagine, before pouring the liquid pure metal into the mold, you have taken the mold to a high temperature. Basically, which we do. Why? Because if you pour the liquid metal into a mold, when the mold is at a low temperature, the mold may get cracked, right? Because of this very high temperature gradient. Thermal shock will be there, right? So now the condition is different. The mold temperature is somewhat close to the molten metal temperature. And liquid metal is poured into the mold just above the fusion temperature, then due to negative thermal gradient. Now the situation will happen that what? A negative thermal gradient will form ahead of the interface, which is created by high latent heat of fusion. So this is one of the reasons. Due to high latent heat of fusion, there will be a negative thermal gradient ahead of the interface, right? Negative thermal gradient means, you understand? Basically, liquid have high temperature, solid have low temperature. But due to this high latent heat of fusion, there will be a negative temperature gradient at the interface. So what happens? This is first image where you can see a protuberance is forming. A bump is forming at the interface. But due to this high latent heat of fusion and negative thermal gradient ahead of the interface, the tip of the protuberance is at a low temperature. That means the tip of this protuberance have a low temperature, means it will not dissolve. It can now grow in that particular direction. But in the first case, the protuberance has been dissolved because liquid temperature was very high. But now the tip of the interface here, tip of this protuberance have a low temperature, right? Due to this negative thermal gradient, due to this high latent heat of fusion, it can easily grow. So now you can see the protuberance has been grown in this particular direction, and some secondary dendrite has been formed. Then further tertiary dendrite will form. The tertiary dendrite and the primary dendrite will be parallel. Okay. So this, due to this kind of situations, you can get a dendritic structure rather than a planar interface. Now, suppose you are dealing with an alloy, or in case of a impure metal. So maximum chance means 100% chance will be there, you will get dendritic structure rather than a planar interface, right? So this, the main reason behind is the solute partitioning. The concept is called solute partitioning, and solute partitioning leads to the constitutional undercooling. I'll discuss that. So what is solute partitioning? Solute partitioning means, suppose you have a impure metal. Impure metals means there will be a base metal and some impurity will be there, right? So when solidification will start, what will happen? Some solute or some impurity may get partition between liquid and solid. That means the concentration of the solute or the impurities will be different upon solidifications. Some solute may be there in liquid, some solute may be there in solid. That means they should be uniformly distributed, but it will not distributed uniformly due to the rejection of the solute by the solid interface into the liquid, right? Similarly, suppose you have an alloy. Alloy means you have a base metal containing lot of alloying element, for example, right? So when solidification will start, what will happen? Some solid will get rejected by the solute, by the solid, and this rejected solute from the solid will go into the liquid. So what will happen? The concentration of the alloying element will be more in the liquid now as compared to the solid due to the rejection during solidification. And you understand liquid can soluble the solutes easily because liquid is at a high temperature, for example. Only solubility of solid will be higher in the liquid. Obviously, we know that. So due to this kind of solute partitioning during solidification, constitutional undercooling will happen. So what is undercooling? Undercooling means, suppose you take a liquid at a particular temperature above its melting point or above its liquidus temperature, right? Suppose you take iron, for example, pure iron. Pure iron is at a temperature of 1539 is the melting point of pure iron, or 1538 degrees centigrade. Fine. You consider you have a pure iron at 1400 degrees centigrade, right? But what is undercooling? Undercooling means sometimes what happen, from 1400 degrees centigrade, the temperature of the liquid iron will reduce to, suppose, 1536 or 1535, right? That is called undercooling. So this kind of undercooling may be happen in the metal, in the alloys or in the impure metal due to constitution. Constitutions means basically due to different components present in the alloy, right? So what basically happens? If you have a question, what is liquidus temperature? You should not be confused. Liquidus temperature means basically we consider liquidus temperature for alloys, for binary components, right? Suppose I have nickel and copper. Nickel melting point is different, copper melting point is different, right? So a liquidus temperature may form at high temperature. Liquidus temperature is the temperature above which everything is liquid. That means below the liquidus temperature, you should understand it should not be completely solid. It may be having solid and liquid both. And there is a temperature called solidus temperature. Below the solidus temperature, everything is solid. Above the liquidus temperature, everything is liquid. That means in between solidus and liquidus, you have both solid and liquid. It is okay. So this kind of temperature are obtained in case of alloys, when we are dealing with alloys, right? But if we have a pure metal, we call it as a melting point only, or fusion temperature. We should not call it as liquidus temperature. Okay, anyways. So what basically happened? This liquidus temperature is dependent on solute concentration, right? That means how much amount of solute is present, that will affect the liquidus temperature. So liquidus temperature may decrease, maybe remain high, depending upon the how much amount of solute is present, right? So as I told, just give an imagination. You have a mold. Now you are pouring a liquid alloy into it, and solidification has started at the wall, for example, wall of the mold, right? And it is growing towards the center of the mold, right? But when the initial solid will form at the mold of the wall of the mold, that solid will reject some solute into the liquid. So what will happen? There will be a what? Concentration gradient will form due to this rejection of some of the solute by the solidified liquid at the mold wall. So concentration of solid will be more in the liquid now. So this leads to the constitutional undercooling. So some portion of the liquid become undercooled automatically. And due to this undercooling, the tree-like structure will form again. Okay? Because when there will be undercooling, obviously at that region only, the solid liquid will become solid. Other regions will be not happening. Right? So lot of dendrites will form in that conditions. Right? But in between the two dendrites, still there will be liquid. Why? Because the solute is getting rejected by the dendrites which is forming, the solid dendrite which is forming. Again, the liquid temperature will reduce, maybe formation of secondary dendrite will happen, then tertiary dendrite. So entire material will full of dendrites at the end. This is one of the best image. Right. This portion is the interdendritic region. This portion is interdendritic region, right? This portion is interdendritic region. So can you people tell me, if dendrites will form, then when entire liquid will become solid, the concentration of solid will be higher in which part? Which region? Tell me.
At the wall of mold.
How it will be at the wall of the mold? Because wall of the mold solidification will start first, and it has rejected the solid into the liquid. The concentration of solid is more in the liquid now, and slowly lot of dendrite is forming. As I told, in between the dendrite there is a space called interdendritic region, which is still in liquid. This last liquid will solidify. So now can you guess in which part of the entire structure having more solid concentration? The interdendritic region, obviously, because this is the last liquid to solidify, and which have got lot of solutes from the solidifying dendrites. Everybody understood now?
Yes, sir.
It is okay? So that means, can you tell me, if an alloy will solidify and give rise to dendritic structure, so this type of structure is good for our properties or bad? Any guesses? The hint is the concentration of solid is not uniform, or the alloying element you have added is not uniform now. So it is good or bad? You might be wrong, no problem. You can guess. The main hint I have given, the concentration of solute is, see, you want to make an alloy, and finally you want alloying elements should be uniformly distributed everywhere upon solidification, right? But when dendrite is forming, there is a preferential growth in particular directions, and due to formation of this kind of dendrite, dendritic arms are forming and interdendritic regions are forming, where still liquid is there, and this liquid will finally solidify, and all the solid will get rejected by this dendritic into the interdendritic regions, and this is the last liquid to solidify. So dendritic structures are good for our properties or bad for our properties?
Sir, good
Bad.
in some cases.
Sorry, can you
Sir,
repeat?
good in some cases, like
Good in
welding.
some cases. It is completely bad. We never want dendritic structures actually, because for, few points are important. First point is what? Dendrites are forming means the growth is not same everywhere. Growth is happening in a preferential direction, right? So that means it is a kind of anisotropy again. Yes or no? You understood my point?
Yes, sir.
Again, anisotropy is forming because the growth is happening in a particular direction, right? Preferential direction. So again, it will give rise to anisotropy. And due to solute rejection, the concentration of solute is not same everywhere in the solid. Somewhere it is high, somewhere it is low. So property will be not good, obviously. Unless until the distribution of solute will be same everywhere, you cannot get same kind of property. The strength may be somewhere high, somewhere low. Or any other properties I am talking about. It will be different. Right? So and again, this, if you remember, coarser grain are good or finer grains are good for our properties?
Finer.
Very good, finer grain. For getting high toughness and high strength, high hardness, we basically need finer grains, basically. So in that conditions, these dendrites are bigger or smaller? Just have a look. Dendrites are big or small? Just have a look. It is growing in a particular direction. It is a big structure, right? Coarser grain again. So coarser, it is a bad. That's why. So one part is related to the directional growth. One limitation is to the directional growth is happening. Second limitation is these are bigger structures. And third limitation is solute concentration is not same everywhere. Fine. So we never want dendritic structure, but anyhow we use the metals which are always contain impurities, or we are basically dealing with alloys. So we will end up with dendritic structures basically. So now if there is a question from your side, so what to do now if we'll get dendrites? Any guesses? What can be done? We have to break these dendritic structures so that we can obtain again equiaxed grain. You understand? This kind of grain. This kind of grains. We always want to have equiaxed grains with random orientations, or they have grown in equal dimension in all axes. I'm talking about individual grain, right? So we want this kind of structure. We never want dendritic structures after solidification. But anyhow, we are obtaining dendritic structure. So what is the solution? Solution is we can do diffusion, so that solute concentration will be uniform and this structure will be baked again. So that can be done at a very high temperature. After solidification, we can put the metal, put this solidified metal into the furnace at a very high temperature, below its melting point. So what will happen? Again, diffusion will start, because you understand the solid will start diffusing at a high temperature. The diffusion will be easy at a high temperature. So solute concentration will be again become uniform, because due to this diffusion, the solid will migrate from high concentration region to low concentration region, and they will be uniformly distributed. And after doing this, you can go for hot forging or hot rolling. So when you roll it or force it, this dendritic structure will break down and it will again become equiaxed grain at the end. That is, in technically the concept is called uh, homogenization annealing, or some people call homogenization only. High temperature homogenization. But this will take a lot of time, maybe 10 hours, 20 hours. That means you have to keep the ingot inside the furnace for 10 hours, 20 hours, 30 hours, depending upon the cross sectional area, right? Because diffusion also takes time. It is not so fast process. But higher is the temperature, higher is the rate of diffusion. You have to remember. Okay, when up to this, you people have understood the formation of planar interface and formation of dendrite. It is okay. Shall I move on? Okay, fine.
Yes, sir.
And this is a very good plot. Huh? This is a plot showing liquidus temperature and distance. This distance is, you understand, starting from the mold wall toward the center of the liquid. And this is the temperature, liquidus temperature. You can see this line is showing you the liquid temp, that is the melting point. It is written temperature of the liquid. Okay, this is the temperature of the liquid, and this line is showing you liquidus temperature. So just have a look. What is happening to the liquidus temperature? Liquidus temperature is going down, right? The liquidus temperature is slowly going down. It has negative slope, right? Why? Due to solute partitioning, as I told, due to constitutional undercooling. Because rejection is happening, solid is getting rejected. So the liquidus temperature is slowly having a negative slope, and finally the temperature is going down, right? And this reason is showing you the undercooled region where solidification will happen. Okay, right now I'll show you a dendritic growth video. Just have a look how dendrites are really forming. So just have a look, how dendrites are growing really. This is a real image. So that means this part is liquid. This part is liquid. And the growth is happening in this particular preferential direction. And this, suppose I'm considering this one. This is the, okay. Just again have a look.
The patch is
Again have a look. Now you people are, can you able to see the primary dendrites, secondary dendrites, tertiary dendrites? Is it visible to you people? Can you people figure it out?
Yes, sir.
The center one, the center dark line is the primary dendrite, right? And the secondary dendrite is perpendicular to it. And tertiary is perpendicular to secondary. Or you can say tertiary dendrite is parallel to the primary dendrite, right? So, and this is completely tree-like structure. Lot of branches are present. Okay, fine. Okay, now the question is, this is a very important topic right now. How solidification of metals or alloy occurs? What is the mechanism? What is the mechanism by which this solidification is happening? Or what is the mechanism behind the conversion of liquid metals alloy into solid metals and alloys? By which process it is happening? We'll discuss that. So there are two steps or two processes. Basically not two process, basically by two-stage process. It is better to say two-stage process. So solidification happens in two stages. The first stage is called nucleation stage, and second stage is called growth stage. Already, which I have shown you earlier. This one. This image. Initially, you have only liquid, but at a random positions inside the liquid, small, tiny crystallite nuclei is forming, which is nothing but a solid, right? So that step is called nucleation. So nucleation is nothing but formation of what? Tiny solid particles inside the liquid. It is okay? Or you can say formation of tiny crystallite nuclei inside the liquid is called nucleation stage. And growth stage means, you can see the atoms will join this particular crystallite nuclei and it is growing, right? That is the growth stage. Right? So just imagine you have completely liquid metal and in the random position some tiny solid nuclei is forming, which is called nucleation stage, and this nuclei is are in a good size, that is called above the critical size. Then they will start growing, and finally it will become grain and grain boundary. So entire liquid will become grain and grain boundary at the end by the nucleation and growth stage. Okay, but condition applied, this nuclei may grow or may dissolve again into the liquid. So what is the conditions? The condition is the nuclei which forms should be in a good size. That should be above the critical size of the nucleus, which we will discuss in the coming lecture, mathematical part. Which already I have written over. Formation of very tiny solid nuclei in the molten metal, which is stable enough to grow into crystal when the temperature of the molten metal goes below the freezing point or liquidus temperature. So you have to remember, nucleation will not start automatically. Nucleation will start when you take the liquid metal below the melting point, for example, or below the liquidus temperature. Why? Because liquid will not remain stable. Liquid is one phase, solid is the other phase. So a particular phase have a particular stability at a particular temperature. So liquid stability is higher at high temperature. That means above the melting point or above the liquidus temperature. But solid is stable below the liquidus temperature or below the melting temperature. So there will be a phase transformation, right, from liquid to solid when we are taking the liquid below the melting point or below the liquidus temperature. It is okay? Now there is this point I already have told you. If nuclei is not stable, it will break down again and dissolve into the liquid. But if it is stable, it will grow. So stability, the growth criteria of the nuclei is what? It should be of bigger size. It should be above the critical size of the nucleus, which we'll discuss that in the coming lecture. Growth stage means the growth of this tiny nuclei into grain or crystal due to addition of atom to them. Fine. Now we'll discuss about the nucleation stage or process. So just have a look. This first image. This entire pink, the light pink color is the liquid. Right? So that means initially we have a liquid only. Now a solid tiny particle is forming, that is nuclei. Right? And this has been grown. And finally it will become grain. And grain boundaries, because each crystal or grain will grow and meet to the adjacent crystal. And that meeting point is nothing but the grain boundaries. If you remember, grain boundary is the defect because the orientation of atom is different in that particular region. Okay. So what is the step? You can see. First step is called clustering. First step is the clustering. First step is the clustering step. What is clustering means? Formation of cluster. How they form? Joining of molecules. So initially we have a liquid. There is no solid particles, but due to when you are taking the liquid below the liquidus temperature or below the melting point, what happens? Undercooling will start. And due to this undercooling of the liquid, at random positions, clustering will happen. Clustering means joining of the molecules. Some molecules will join and become clusters, solid molecules, right? Then nucleation will happen. Nucleation means formation of the nuclei. So these clusters will join to form nuclei due to joining of the cluster. Okay. Finally, this nuclei will grow. That means each crystal grows and form grain and grain boundaries. I think it is okay up to this. Or shall I repeat? Okay, let me tell it again. Just imagine you have a mold containing a liquid, and you are taking the liquid to below the melting point or below its freezing point, or you can say below its liquidus temperature. So what will happen? At a random positions, some cluster of solid will form. How they will form? Due to joining of the molecules. And this cluster will then combine to become a nuclei. And this nuclei should be bigger enough. Its size should be above the critical size of the nuclei. So if this condition will fulfill, this nuclei will start growing and become individual what? Crystals or individual grains. And when this individual grain will grow or crystal will grow, they will meet to the new grains adjacent to it, and finally you will end up with grain and grain boundaries, which is the structure over here. Fine. Now we have two types of nucleation, primary nucleation and secondary nucleation. Secondary nucleation means, suppose you are dealing with a pure metal, suppose pure iron. Initially at the mold wall, solidification will start, the solid iron will form along the mold wall, and new nuclei will form on these solid particles of this iron. That is called secondary nucleation. Right? But what is primary nucleation? Primary nucleation are two types, homogeneous and heterogeneous, which we'll discuss. Homogeneous nucleation. So what is exactly homogeneous nucleation? As I told, nucleation means formation of tiny solid particles inside the liquid. It's called nucleation, right? So, or formation of tiny solid crystallites. Okay. So homogeneous means it is same everywhere, right? So if the probability of formation of nuclei is same everywhere inside the liquid or inside the mold, it is same everywhere, that is called homogeneous nucleation. Okay. And homogeneous nucleation do not require any kind of foreign particles or impurities for nucleation. You have to remember. And homogeneous nucleation is a spontaneous process, right? Homogeneous nucleation is a spontaneous process. Automatically it will happen. It do not require any kind of foreign particles inside it. Suppose you have a liquid, you add some foreign particles or some alloying elements, which are solids. So what will happen? Nucleation may start on these foreign particles itself. So these sites are nothing but the heterogeneous sites. And this kind of nucleation is called heterogeneous nucleation. So that means for heterogeneous nucleation to occur, you are intentionally adding some foreign particles or impurities into the molten metal or molten alloy, or the mold wall itself will act as a nucleation site. Right, mold wall. Right. So that means for heterogeneous nucleation, we have certain preferential sites where the nucleation will start preferentially. Or in other way, I can say probability of nucleation is not same everywhere. It is higher along the mold wall, or maybe if some impurities are present or some alloying element are present, which are solid, which have high melting point, right? So those are called heterogeneous nucleation. So can you tell me which nucleation will be easy or which nucleation will require less amount of energy? Or driving force is higher in which case?
Homogeneous.
Homogeneous nucleation is easy.
Homogeneous.
Anybody want to speak anything else? You have to give the justification. Few minutes before I have shown you a slide where I have shown the solidification is starting along the mold wall. It is not happening everywhere. And after starting of the solidification along the mold wall, it is growing toward the center of the liquid. So which nucleation will be easy? Or which nucleation requires less amount of energy? Obviously, those kind of nucleation which requires less kind of energy, that will be favorable. Obviously, heterogeneous nucleation, right? Because heterogeneous nucleation is happening along some preferential sites like mold wall, because mold wall have very low temperature compared to the inside the mold, right? Heat dissipation will be easy to the environment. Solidification will start because less energy is required over there, right? Similarly, if you have added some foreign particles which have high melting point, they are still solid present. So a new solid may form if a initial solid will be there, easy, right? That means the liquid will try to solidify on that particular solid which is still solid in that particular area, right? So heterogeneous nucleation requires less amount of energy. Or in other way, can you people tell me, if I will talk about undercooling, which one will require more undercooling and which one will require less undercooling? Heterogeneous nucleation will require more undercooling or homogeneous nucleation will require more undercooling? Let me see who can answer. Undercooling means you are taking the molten metal or alloy below the liquidus temperature or below the melting point or freezing point. Or both will require same undercooling. Shall I repeat my question if you want? Okay, my question was, you have a liquid which is poured inside a mold and you want to do solidification, and you have already understood solidification happens in two stages. First stage is the nucleation stage and second stage is the growth stage. In the nucleation stage, a tiny solid particle will start forming and it will grow into grain structure or grain boundaries finally, right? So, and we have two types of nucleation: heterogeneous nucleation and homogeneous nucleation. So now tell me, and to do solidification, you always need undercooling, basically. Undercooling means unless until you bring the molten metal or molten alloy below the melting point or below the liquidus temperature, solidification will not start, right? So anyhow, you need undercooling. So undercooling will be required same for both kind of nucleation, or it will be higher for certain kind of nucleation or lower for certain kind of nucleation. Or in other way, I can ask, for homogeneous nucleation, you need more undercooling or less undercooling? Or similarly, for heterogeneous nucleation, you need more undercooling or less undercooling? Or for both kind of nucleation, we need same kind of undercooling? Already I have given you a hint. Heterogeneous nucleation requires less amount of energy. A driving force is easily available because mold wall is present. Or if you have any impurity particles, solid impurity particles. So which will require more undercooling or less undercooling?
Homogeneous will require.
Homogeneous nucleation.
Require more or less?
More.
More.
Very good. Excellent. So you understand homogeneous nucleation means the probability of nucleation is same everywhere. Anywhere in the mold, it may be the center of the mold, it may be the wall of the mold, everywhere the nucleation probability is same. Right? But it is not exactly happening in the real situation. In the real situation, solidification starts at the mold wall. And mold wall is the preferential site for the nucleation because the energy availability is there already. You need a less driving force for that. Oh, sorry, high driving force is available, you need a less amount of energy, right? But in case of homogeneous nucleation, you need more amount of energy, right? So obviously, when you want to do homogeneous nucleation, you have to go for more undercooling. If you go for more undercooling, driving force will be available, solidification will start, right? So basically, that means what is the conclusion? Conclusion is heterogeneous nucleation will be easy always because it requires less amount of energy because driving force is already available along the mold wall, or if any solid impurities is present or solid alloying element is present, right? Which already I have discussed is written over here. Huh? For heterogeneous nucleation, location of nucleation site is mold wall, insoluble impurities, insoluble alloying element, if any, who lower down the energy required for the nucleation to happen. These are the location of heterogeneous nucleation sites. For this addition of foreign particles, nucleating agents, you have to remember, if you are intentionally adding some alloying element, some impurities element, or some foreign particles into the liquid to start the solidification or to start the nucleation stage, those particles are called nucleating agent or inoculant. In the gate examination, a lot of questions will may be there from this part. Are required, which is intentionally added to the liquid metal, so that nucleation will happen on them. Here, surface energy required to form nuclei is less on the foreign particles compared to the inside the liquid itself. So this is the reason behind the easy of the heterogeneous nucleation, because here surface energy required to form nuclei is less, right? Here, large undercooling, supercooling is not required for solidification to start. I think up to this part it is clear, or you have any questions? If you have any questions, we can discuss. Otherwise, it will be not good to explain further. You can ask me any questions related to heterogeneous nucleation, homogeneous nucleation. Anybody have any questions? You can ask me. You are free to ask. Okay, fine. I think things are clear to you. Now we'll discuss about the grain structure in casting ingot. Without foreign particles, inoculants, right? So that means now just have an imagination. You have uh, two molds. You have two molds. You have same metal. Suppose you have same steel, for example, fine, or let it be a cast iron. You have molten cast iron, and you have two molds. In the first mold, you are pouring the molten cast iron. In the second mold, you are pouring the molten cast iron, and intentionally you are adding some silicon or some silicon carbides or some alloying elements or some foreign particles. But in the first mold, you are not adding any kind of foreign particles. So now tell me, now I'll show you which kind of solidified grain structure will form. Just this is the first image. So this is a mold. This is an image of a mold. This is an image of a mold. Entire is liquid. And now just see, due to heterogeneous nucleation along the mold wall, some nuclei have formed. Right? These are the nuclei which has formed and grown into crystals. This is called equiaxed grain, if you remember. Equiaxed grain means they have grown in the same manner in all direction and they have a random orientation. Fine. This is the same image again. You have a mold having liquid and solidification starts from the mold wall and now growing towards the center of the liquid. Right. So this is the equiaxed grain. And near to the equiaxed grain, you have columnar grain. You have to remember. This grain near to the equiaxed grain are called columnar grain. Columnar grains means they are like columns. Like columns are oriented in a particular directions. They are long basically, long and they have grown in a particular direction. So these are columnar grains. So first grain which has formed along the mold wall is called equiaxed grain, which is small in size, but adjacent to the equiaxed grain, we have columnar grains. Columnar grains are preferential, they have preferential orientations. They have oriented towards the center of the mold. Okay. In this direction, they are left to right. Here, they are right to left. At the bottom, that is bottom to top direction. Okay. And columnar grains are bigger in directions. Dendritic, like dendritic structures, they have preferred orientations. The columnar grains have preferred orientation. And columnar grains are bigger grains actually. Long and bigger grains. You have to remember, columnar grains are long and bigger grains. So finally, solidification is complete. You can see what is the structure of what this is actually called macro structure of the ingot. So you can see we have three reasons. The first reason is along the mold wall. The second reason is adjacent to the mold wall. Adjacent to the equiaxed grain part. And finally, at the center, you have a new structure. Complete entire center of the mold is having a new structure. So along the mold wall, we have equiaxed grain, small and equiaxed grain. Then after that, we have columnar grains, which are long and big, and they have preferred orientations. And finally, at the center of the mold, we have large and which kind of grain? Can you tell me, anybody tell me which kind of grain is present at the center?
Equiaxed.
Very good. They are again equiaxed, but what is the difference between this equiaxed and this equiaxed? Along the mold wall, you have equiaxed grain, and at the center also you have seen it is equiaxed. But what is the difference? This equiaxed and this equiaxed. What is the difference? These are bigger. It is clearly visible. Yes or no? These equiaxed grain at the center are bigger grain size. Anybody guess why they are bigger? Because they have been grown into bigger size, right? Because temperature is higher at the center of the mold. It is okay? When there will be high temperature, the things will grow into bigger size. The solid always try to bigger when the temperature is available. So similarly, the grain may become bigger and bigger with increasing in the temperature. Okay, can you people tell me what is the direction of heat rejection? What is the direction of heat rejection? And after saying the direction of heat rejection in the mold, heat rejections means heat will be rejected, fine. So that solidification will happen. So that the temperature can be lowered and solidification will start. Okay. So what is the direction of heat rejection and what is the relation of the direction of heat rejection with the columnar grain direction? Let me see who can answer. What is the direction of heat rejection in the mold or inside the mold? And second question is, what is the relationship between the heat rejection inside the mold with the direction of the columnar grains? Obviously, the direction of heat rejection will be from the center of the mold to the wall of the mold. Yes or no? Because finally the heat should be
Yes, sir.
dissipated to the environment. The mold wall is attached to the environment itself. The heat should be rejected from the mold wall to the environment. Where the heat will come? It will come from the center of the liquid, center of the mold, and it will move from the center of the mold to the wall of the mold, and from wall of the mold to the atmosphere or to the environment. So now can you relate the direction of the columnar grain and direction of the heat rejection? They're same or opposite or perpendicular or what?
They're same.
Okay, let me repeat again. The heat rejection direction is starting from the center of the mold towards the wall of the mold. Then from wall of the mold to the atmosphere. In this way, heat is getting rejected. And just have a look, carefully look at the mold and look at the columnar grain directions.
So it will be opposite, sir.
Obviously
From
opposite.
bounded to
Obviously opposite. This is the center of the mold, right? This is still, that's the temperature is very high. That's why still it is in liquid state. But along the mold wall, the temperature is very low because mold wall is in contact with the atmosphere. That's why solidification is happening along the mold wall first. There is no increase, right? And solidification is moving toward the center, right? So obviously the columnar grain is growing from the mold wall towards the center of the liquid, but the heat is getting rejected from the center of the liquid towards the mold wall. So it is just opposite, right? So finally, let me tell you again an important point. These the equiaxed small equiaxed grain which forms along the mold wall are also called chilled zone, because this is a very chilled region, because the mold wall is in contact with the atmosphere, right? That's why equiaxed. Huh? I think up to this it is clear. If somebody will ask you, you will take a mold and you will pour a molten metal, how the structure will obtain, you can explain it now.
Excuse me, sir.
Yes.
Sir, why equiaxed grains are created in the center? The columnar grains can meet each other in the
Okay,
center.
fine. Yeah, that may be situation. That may be situations. See, as I told already, sometimes what happens, this columnar grain can be compared with the dendrites again. Yes or no? Okay.
Yes.
It may compare with dendrites because dendrites also grows in a preferred direction. They are also big. They are also directional. Columnar grains are also big. They are also directional. But difference between columnar grain and dendrite is what? Columnar grains are uniform, right? Like a column completely. They have equal dimension, right? I'm talking about the thickness or width, right? But dendrite is a tree-like structure. It is forming branches. Lot of branches is coming out. But in columnar grain, there is no branches. A single grain is going in a particular direction, right? So that can be happen. The columnar grain can consume the entire liquid, but that depends upon the material you are handling. If you're using a pure metal, that may happen, no problem, right? If you're using a pure metal, that may happen sometimes. But if you're using an alloy and solute is getting rejected, right? Solute is getting rejected where? So just imagine you have a mold and you are pouring a liquid metal, and solute is getting rejected from the mold wall to the center. So finally, the concentration of solute will be higher where? At the center of the liquid, obviously. Yes or no?
Yes, sir.
Obviously, the center of the liquid will having higher concentration of solute because the solidification is starting from the mold wall towards the center. And due to solidification, the solute is getting rejected by the solid to the liquid. So finally, the liquid will solidify at the center, right? So if some solid particles will be there, if suppose consider the solids are solid particles now. So what will happen? Solidification will start everywhere. I told you just before heterogeneous nucleation. If some solid particles will be present on that solid particles, the liquid may become solid again. Nucleation will start. So that means everywhere nucleation is starting. That's why equiax grain is coming out. It is okay now? So equiax grain will form if you are adding foreign particles or if heterogeneous nucleation is happening actually. Basically, because in the real situation, if you look, homogeneous nucleation is very difficult. It is not happened actually in the real situation. Okay, basically homogeneous nucleation do not happen in the real situation. Always heterogeneous nucleation happens because nucleation always start at the mold wall, or it will start if some solid particles are present as an impurity or alloying elements, because energy requirement for heterogeneous nucleation is less because a new surface has to form. When a new surface has to form, if surface energy is less, then obviously the surface will grow or it may form easily. Okay, I'll show you a structure here. The same thing I will show you here. Just have a look. So which kind of structure is this? Columnar or equiaxed or what?
Equiaxed.
Equiaxed, very good. See what I have written, equiaxed grain structure. Grain with random orientations, an addition of nucleating agent to molten metal or alloy just before solidifications. So that means, okay, uh, that means again, if I will ask, uh, columnar grains are good for our metals or equiaxed grains are good for our metals or alloys? As I have told,
Equiaxed.
obviously equiaxed. Why? Because they are of nearly same dimension. They have grown equally in all directions and they have random orientations. Fine, no problem. But columnar grains are what? They are elongated grains, bigger grains, and they have a directional property. So an isotrope. So this will give you isotropic property. But if columnar grains will be there, they may give you what? An isotropic property, right? Now, nucleating agents. So, nucleating agents are also called inoculant, as I have told, which are nothing but the foreign particles, which are intentionally added to the liquid alloys so that heterogeneous nucleation can start everywhere. And you will end up with what? Equiaxed grain. So, you have to remember this point. First point, important point is what? We always require equiaxed grain in our metals or alloys during solidification. Okay. So, how to get that? It is very difficult because, as I told, everywhere nucleation will not start. Nucleation will start along the mold wall. If nucleation will start along the mold wall, then first equiaxed grain will form, but again it will further new grains will be columnar one, right? But we want everywhere we should have equiaxed grain. So that is why intentionally we are adding some foreign particles, so that when foreign particles will go, you can homogenize it by stirring or some mechanical stirring something, so that all these particles will uniformly distributed inside the liquid, which are still solid particles. So on that solid particles, nucleation will start everywhere. So if nucleation, just imagine a situation where nucleation is starting everywhere in the mold, not along the mold wall only, everywhere. So what will happen? Each nuclei will become a grain, and each grain will meet and become a grain boundary. So finally, you will end up with equiaxed grain. There will be no columnar grains. It is okay now up to this?
Yes, sir.
Yes,
So
sir.
Yes, sir.
these are the, yes. Any questions you have? Okay, these are the nucleating agents technically used in the industry. For a particular alloy, we use a particular kind of nucleating agent. We cannot randomly use any kind of nucleating agent, right? Or inoculants. For aluminum alloys, we are using titanium compounds like TiAl3, TiB2, like titanium carbide, titanium diboride, titanium aluminide, right? For cast iron, we are using sulfur compounds. Like for example, sometimes we add silicon carbides, or any sulfide, right? For magnesium, we are using this kind of thing. Stainless steel, we are using this kind of thing, right? So these things are added into the molten alloys so that we can obtain homogeneous structure. Equiax structure are homogeneous one actually. They will give you homogeneous property. Okay, so a few minutes before somebody have asked the same question, right? Just have a look. Can you people tell me, in between these three structures, macro structures of the ingot, these are three ingots. Huh? Which one is the best? Which ingot will give you the best property or good property? In
Third
between
one,
these
Third one, sir.
third one, very good. Why?
because
Because
of
it's
equivalent structure.
equal structure.
Because of the equiax grain structure. Okay, fine. If you have a equiax grain structure, then what will happen to the property? The entire body will have which kind of property? Isotropic? Yes or no?
Yes, sir.
Right? But here, what is the problem, and here what is the problem in these two? In these two cases, you have different grains. Initially, along the mold wall, we have small equiax grain. Then we have long columnar grains. But here we have along the mold wall, we have small equiax grain, then long columnar grains, then big equiax grain. So property will be different in different reasons. That means if you take this ingot and you measure the hardness along this portion, along this portion, along this portion, the hardness value will be completely different. If you take a piece of metal from this portion, and this portion, you measure the strength will be different. So there will be a completely anisotropic property will be there, right? So can you tell me from this mold, in which mold we have intentionally added the inoculant or nucleating agents to
Third
do
one, sir.
solidification? Third
Third
one,
one.
very good, third one. And in these two cases, we haven't added anything, basically. The same image has been magnified and shown over here. Just have a look. My macrostructures of ingot with and without inoculants or foreign particles or nucleating agents. Huh. Just have a look. So this is equiax grain only. This is small equiax grain and columnar grains. This is small equiax grain, columnar grain, and big equiax grain. Right. So this is always we want in our materials at the end. So if somebody will ask why we add foreign particles into the molten metal, we are intentionally actually adding so that we can get a equiax grain structure. Why? Because we want heterogeneous nucleation to happen everywhere, like homogeneous nucleation. And we'll end up with this kind of structure. Okay. Okay, I will end this lecture over right now. Any questions you have, any technical questions you have, you can ask me, or any silly questions you have, we can discuss it.